Good morning, everyone. It's June and it's still pretty crappy and cold weather outside, so my throat is trying to cope. But let's make the best out of it. And what better day than to actually be recording a nice lecture this week on flow, field, and context-sensitive pointer analysis with Boomerang. So this set of terms might sound very convoluted, but actually this is a really interesting breakthrough because in a relatively, well, to some extent disappointing paper some years ago, Tom Reps actually was able to show that it's impossible to implement pointer analysis and, well, in particular, field-sensitive, flow-sensitive analysis because that's actually undecidable. And I will give you some further insights today about why that actually is. But we came up with a design a few years ago that implements a flow, field, and context-sensitive pointer analysis nonetheless. So it's not fully flow and context-sensitive, but to a very large extent. And that actually has some very nice properties, as I will explain in detail in this week. So what is this Boomerang solution or algorithm all about? It's basically a points-to analysis, but based on push-down systems. And to continue our discussion from the previous week, it is based on the demand-driven design. So it basically answers points-to queries. What may variable X actually point to? And because it's demand-driven, it computes only the necessary data flow graph relevant for the query. And like I already said, it has these properties, so it combines context, field, and flow sensitivity all together to some very large extent. So let me show you a little bit of an example of a example program that we may want to discuss just for the purpose of illustration. So let's assume this is a Java program. And we are initializing two objects at two allocation sites. So here at line 2 and here at line 4. And on the right-hand side, just as it's shown in the debugger, we have a current runtime view of the heap. Okay. And now we can assume that, for instance, we're executing this particular statement here. So we are assigning B the object in A, and that, for instance, will then actually, initialize this object reference here to object O2 that has already been assigned to A, right? Now at the next statement here, we're actually initializing variable X with the object in O4 or allocated at O4. And then here, now it becomes interesting. We are actually assigning this object in X to B.F. Why does that become interesting? Well, at this point, B is already aliased with A, right? Because of this assignment statement here. So both B and A are actually the same object. So that means we are not actually only updating B.F, as you see here, but we are also updating A.F. And as a consequence, then down here, you will find out that then actually X and Y, they will also alias, right? So when I now move forward here, you will see that Y is actually loading A.F, and this then constitutes an alias between the two. So what does this tell us? It tells us whenever we have a heap assignment, we need to know about all the different aliases of the owning object, right? So of the base object, that's also the terminology that's typically used in papers. So this is the base object or base reference of this field access. And we need to know all aliases of this base object in order to decide what possible aliases exist. And then the static analysis must potentially also update the respective information. Now, assume that we wanted to implement a flow-sensitive and context-sensitive pointer analysis for Java. And let us further assume that for efficiency reasons, we wish to implement this using IFDS or, sorry, this shouldn't be PDF, this should be PDS, pushdown systems. So using distributive formulation, right? So we've already seen that if you implement things in IFDS or pushdown systems, you need to have a distributive framework, or you need to have a distributive formulation of your problem so that it fits this framework. And if we try to do this, this could look as follows. So again, here we have the same example program, okay? And now on the right-hand side, let us assume that we have used, in this case, IFDS to keep things simple in order to model possible data flows, or in this case, it's actually object flows or pointer flows in the extended supergraph, okay? And so for instance, this is now the data flow that relates particularly to the object 04, right? So in this exploded supergraph here, we are only considering data flows for that particular allocation site. And where does it start? Well, at this point, it's being assigned to variable x. And obviously, that also remains assigned to x until the next statement. But then at the next statement, we see that this is also being assigned to b.f. That's why we are generating the fact b.f here to basically tell the analysis that also b.f is sort of tainted now, right? Which in this case means it's also pointing to this 04 object. And then this propagates further, right? So this statement here, it doesn't really manipulate that particular pointer any further. But what you will see here is that this is obviously missing something, right? So the naive analysis that we have here, it fails to take into account, namely the aliasing of A and B here, right? So that to some extent has to do also with the sort of demand-driven nature, right? So, and also with the fact that here we are assuming that we are keeping track of all these allocation sites separately. And that's really what makes up or what defines a distributive problem, right? So in a distributive problem, we're really considering each data flow fact in isolation. And so here that means we are really considering each allocation site in isolation, but the allocation site is at line 4, and it starts being tracked at line 4 in a demand-driven way. But that basically means that this aliasing that is constituted by line 3 here, it's never even observed by the analysis, right? But even if for some obscure reason we were to start the analysis earlier, like here, if it's only with respect to this particular allocation site, it wouldn't necessarily pick up on this aliasing here because it's not really related directly to this allocation site, right? So the thing is, there's obviously something missing in this analysis, right? And if we were to encode it as such, that would be incomplete and therefore unsound because we would be missing this crucial assignment here. We would never learn that X and Y can actually alias as well. Now, why is this? I mean, there's a very conceptual underlying problem that exists here. So the thing is that flow-sensitive pointer analysis, and this has been proven years ago, that's actually not distributive. And the problem is that if we had a correct flow function for this particular statement here, so for this one at line 5, then this would actually, for this particular statement, it would read like this. So we would have to say for all aliases A of B, right? So for all aliases of this base object here, generate A.F. So we need to have an all quantification of all these aliases, right? So we're basically looking for all the variables in the program that might be substitute-based variables here, which may point to the same object that B is known to point to, okay? And for all of these, we actually generate then A.F. Now the problem is that this all quantification, this really turns this into a non-distributive problem. And in fact, I've already shown this in DECA 1, right? So in DECA 1, we have discussed the counterexample of non-distributivity. So there I showed you that there are certain cases that you can construct that illustrate that this is not distributive, because there were cases where you basically, on the one hand, you can either first merge and then actually execute your flow function, and then you will get a result that's different from when you first execute your separate flow functions and then actually constitute a merge. And that's exactly what what defines non-distributivity, right? So if it had been a distributive problem, the results would have had to be identical. And so we know that we cannot fully solve this problem in a distributive framework, right? That's simply impossible. But the main idea behind Boomerang is now that although we know that we cannot solve this problem using a distributive framework such as IFDS, IDE, or pushdown systems, or even weighted pushdown systems alone, we can also observe that we could solve the problem if these frameworks, if the alias information that the pointer analysis itself requires had already been resolved, right? So in the previous picture that I showed you, if at the point where we assign something to b.f, we already know these aliases, then we can simply plug in the solution and we can just make use of it. And then actually regular distributive propagation is sufficient, because all the non-distributive parts have sort of been projected away, right? They are done by somebody else. So the idea is that we want to make that assumption explicit through a recursive design and demand-driven queries. That means whenever the analysis requires alias information, it will issue a subquery to compute it. And then it will incorporate the results back into the distributive analysis. And what's interesting and important is that actually these individual subqueries, as I will show you in a few minutes, these themselves can also be distributive. So that means really the largest extent of the computation actually is distributive, although the framework as a whole is not. So, but nonetheless, this makes it pretty precise and efficient, because all the subproblems can actually be solved by a distributive solver, so without any loss of precision, and also obviously very efficiently. And this is really extremely efficient because we are tracking individual pointers separately. And that's actually largely different from pretty much all the other alias analysis that existed earlier, because pretty much any other design I've seen in terms of alias analysis will use alias sets. And whenever you have sets, you have a power set domain that is very large. It's, with large domains, it's not a good idea to put them into a distributive solver because they require not only finite, but typically very small problems with small domains. And so we, or I should say actually really Johannes Späth, my PhD student who came up with this idea, he really made this work for these kinds of solvers. So let's take a look at how this works. Again, the previous example that I already shown you, right? And we would propagate this further down here. But now actually at this particular point, and that's the important part, at line 5, we would actually issue a subquery. We would query for may aliases of the space object B, okay, or the space variable B. And now, what would that entail? I told you that this is a demand-driven analysis, right? And so you would probably expect that this is now issuing a backward query or a backward analysis, and that's exactly what's happening here. So we would be starting a backward query for B, and now we would search backward to see to search for any statement that assigns B. and we will find such a statement at line 3, right? And this basically well, causes this arrow here to be drawn, right? So we know that the value of B came from A, and this is now actually also killing B, and it's generating A. Why is it killing B? Because B actually had no value earlier, right? So B is being assigned one value here, and that value is guaranteed to come from A. It could not have come from anywhere else. So that's why this is being killed and A is being generated. And likewise here, this value that is stored in A here, it could only have come from this allocation side, right? And so that's what we see here. And this is also what now terminates this backward analysis. So we will search backward until we find an allocation side. And sometimes there might be ambiguity, right? So there might be ambiguous assignments. For instance, if we have an if-then-else statement or so, we don't quite know which allocation side this variable was initialized with. So there might be multiple options, but then we will search until we have discovered all these allocation sites, and each path will terminate on its own when an allocation site is reached. And that is the backward analysis of the demand-driven design. And now you have already learned what happens now when this backward analysis terminates. Well, it conducts another forward analysis, a forward pass with the allocation site that has been found, right? So in this case with O2. And we will now compute this demand flow of O2. And this will then actually answer the query that was originally issued. So we see that O2, initially it's assigned to A, so that's our starting variable. And now we're essentially conducting a taint analysis. So it's essentially using IFDS, you could say, right, or pushdown systems to actually propagate this further. And we can see that A is now also being assigned to B. And then essentially that doesn't change anymore, right? So we don't touch A and B anymore. And now in particular, when the analysis now reaches this statement here, it's actually set up to answer the original query, right? And so the analysis will then have identified that it has now reached this statement with all its possible data flows, right? And it will then return to the analysis that originally issued this query, so to this thread, so to say here. It will issue the result that A and B can actually alias. That can be found out by simply knowing that they are part of the same graph here, basically. And it will even return the additional information that both of these variables, they actually may point to O2. At this point, that's probably not very relevant, but there may be other analyses that are actually interested in knowing exactly which allocation side one is talking about. Here, it's actually sufficient for us to simply know about the aliasing relationship. So we will have learned that A and B, in fact, may alias at this statement. And that's actually the important fact that we are after here. Now, it's up to the original analysis that issued the query to make use of that particular information. What is a sensible way to make use of that information? Well, looking at the statement, knowing that A and B may alias, what do we want to do? We want to say that not only B.f, but also A.f might actually point to this particular object here, to O4, right? And keep in mind that this is actually the data flow graph for O4. So what's happening now, and this is again the design that we chose here, we will add an additional edge here. You will see that this is a non-standard edge, right? It's from one statement to the same statement, right? Which is unusual in IFDS, but it's just the way that we use to model this. So here we are basically generating A.f as well, right? And this is such an aliasing edge that we introduce here. And this is really the only thing that is needed that that is sort of outside of the scope of IFDS. In IFDS, you cannot draw such an edge, and in pushdown systems, in the bare pushdown systems algorithm, you cannot really draw such an edge. It's simply not allowed, right? And in particular, that there wouldn't be any backward and forward passes and so on, that we needed to be able to actually determine that this edge is necessary, right? So this is where it also gets non-distributive, right? Because here we have this all quantification, so we need to find all the aliases, and for each alias we draw such an edge. But the rest then, these gray edges here in particular, they are again standard IFDS or standard pushdown systems algorithmics, right? So we will simply generate this here, and that's that. And then the rest here, it's simple standard processing of this particular statement at line 6, right? Now, because a.f has been sort of tainted, right? We know that it carries this particular object. And because a.f is being assigned to y, for instance, this edge here will be drawn. Okay. So that's really all that's to it, right? So we incorporate the answer and then propagate further. Now, again, why is this interesting? In fact, I think it's a really brilliant design because each individual analysis in Boomerang is actually distributive, right? So we've seen this. We've seen the first forward pass. All the gray edges are distributive. Then we've seen the backward pass that was also distributive. So we never left the distributive framework here. And we saw the sort of third forward pass that was propagating these allocation sites further. That was again distributive, right? So we have these forward and backward passes, and they're each doing their own thing, and each single pass is actually distributive, except for these points where we need to actually issue these subqueries. And these are so-called points of indirections. Points of indirection, that's what we call them in the paper. And at these points, where you have these indirect accesses, Boomerang then issues these subqueries, and then once answered, they return all possible aliases, and these are then incorporated. And this actually allows Boomerang to solve the non-distributive problem, the non-distributive demands in these places of the analyzed program. And yeah, the large advantage is, of course, that to the largest extent possible, I would say, Boomerang's analyses are distributive, and therefore they can be solved efficiently for the most part, and they can also be solved, and that's also very important, actually pretty precisely for the most part, right? Because as you know, when you have a distributed solver, there's no need to approximate in terms of recursion and so on. So that's all really nice, right? And like I also told you, there are no alias sets, so all aliases are tracked individually, and that makes for a nice and small domain. So you would think this is really perfect, right? Like, can it get any better? And in fact, we had implemented Boomerang on top of IFDS some years ago, and we had published this at ECOP, one of our actually top conferences. And then we found nonetheless that there was still some open issues. So let us talk a little bit more about this. The thing is, something we haven't really talked about is field sensitivity and modeling fields in data flow analysis. And the modeling I've showed you so far was using access paths, right? And you know that an access path is actually a local variable and a sequence of field accesses, right? So here it's a very simple sequence, just a single field access. But on the next slide, I will actually show you some more complex ones. Because the problem is that these access paths, they can grow, right? And here there's just a simple example program, for instance, where we have some cascading. So here we are actually assigning this object stored in B to a.f, but then we're actually generating a new object C, and then its field C.G is actually assigned A. And so now we have a field access expression C.G.f, this one here, that is also being assigned the original object, right? And We already discussed this in DECA 1. These access paths, they can grow. And the problem is, because in pretty much any substantial program, you will have loops and you will have recursion. And in many programs, you will also have linked and recursively linked data structures. You can get such growth like you see here very easily, right? So here we are assigning one of these objects that we are tracking recursively to this A field. And as you will see, the further we go to this loop, this will continue growing and growing. And we have already discussed also in DECA 1 ways to deal with this, right? So one possible solution is basically a widening, right? So a k-limited access path that simply tells you, okay, after 3 or 4 steps or so, or maybe even just after 1 step, you simply widen and abstract away all the rest of the access path. So you replace this, for instance, by c.a.star or simply by representative c.a. And that will then allow you to terminate, right? Because now you have a finite domain again, so that's really essential. And depending on how long you set this parameter k to bound your access paths, you might even get a relatively small domain. But of course, there is a caveat, right? Because now we have artificially bounded this domain, and we are of course approximating, right? Because this additional information here about how the access paths would normally continue, that is simply lost, right? And so now, for instance, the access path c.a.a.a and c.a.a.b, they would be merged to one and the same representative, and the analysis would no longer be able to distinguish one from the other. And that then actually led us to think about another kind of design, and that will also model field accesses, essentially through a sort of IFDS problem, but in this case, it's really essential to actually model it through a pushdown system. Because that has some advantage of making this or finite, as I will show you in the next video. Talk to you then.